For the first time in over half a century, humans are heading back to deep space. Rising off Kennedy Space Center's Pad 39B, the Space Launch System produces almost 9 million pounds of thrust to push Orion off the Earth. Artemis 2 is a high-stakes engineering stress test. NASA is sending a crew to push the capsule's hardware to its design limits under real flight conditions. Inside, 4 astronauts, Reid Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, absorb intense physical vibrations. As the rocket climbs, it punches through max Q, the point of maximum aerodynamic stress, where the atmosphere fights back hardest against the ascending vehicle. About 2 minutes into flight, having delivered the necessary thrust to escape the thick lower atmosphere, the twin solid rocket boosters separate. Shortly after, the launch abort system is jettisoned, and the core stage completes the push into low Earth orbit. Surviving the massive physical forces of ascent is just the baseline requirement to get off the ground. The true test of keeping human beings alive begins once they hit the vacuum of space. Almost immediately, the harsh environment starts messing with the hardware. About 51 minutes into the flight, during a planned satellite handover, a configuration glitch causes a temporary loss of communications. Down below, Mission Control also realizes they have a broken toilet controller to troubleshoot. The severe shaking of launch physically rattles a crossover valve on the water tanks, forcing it closed when it should be open. And as they leave the atmosphere, transient bursts of space radiation trigger latching current limiter failures, essentially tripping the electronic breakers on the spacecraft. A computer can't always diagnose a rattled valve or a glitching comms link. These unpredictable real-world mechanical faults are exactly why human operators are flying this mission. They are there to work the problems. Before they can safely head to the moon, the crew spends their first day in orbit, putting the ship through its paces. Orion separates from the spent upper rocket stage, but instead of flying away, uses it as a target. The astronauts take manual control of the spacecraft to see how it handles. They practice precise, multi-axis maneuvers, flying laterally, managing controlled rotations, and hovering mere meters away from the discarded stage. These manual maneuvers simulate the precise docking procedures required for future lunar landings. Before Orion can safely connect with a SpaceX Starship or the Blue Moon lander shown here, pilots must master the capsule's response to subtle lateral and rotational inputs. Proving they can precisely command the ship at close range is the final hurdle. Only after the capsule passes this handling test will Mission Control clear them to fire the engine for the trans-lunar injection, the burn that sends them out of Earth's orbit. This diagram illustrates a free return trajectory. It is a carefully calculated orbital path that uses the moon's gravity to capture the spacecraft, swing it around the far side, and slingshot it directly back toward Earth, without requiring the main engines to fire again. As the spacecraft travels hundreds of thousands of kilometers down this path, the standard satellite arrays closer to home lose their reach. Communication relies entirely on NASA's Deep Space Network, massive radio antennas in California, Spain, and Australia tracking the capsule. Inside the cabin, the crew strips off their pressure suits and gets to work. They evaluate mobility, test emergency pressurization features, and constantly monitor how much radiation they absorb now that they've left Earth's protective magnetic field. The 4-day transit to the moon is a constant grind of medical and technical evaluations. They are actively mapping the exact limits of both human biology and mechanical endurance in the deep space void. Unlike the Apollo missions that entered a tight, low lunar orbit just 110 kilometers above the surface, Artemis 2 is taking a wider path. Orion will swing past the lunar far side at a massive altitude of 8,000 kilometers. At that exact moment, the 4 crew members will be farther out in the solar system than any humans in history. Looking back, Earth will be a tiny dot sitting 370,000 kilometers away. Passing directly behind the bulk of the moon, severs all radio contact with Earth for nearly an hour. The crew and the spacecraft are completely isolated. This total blackout forces the Orion capsule to operate autonomously, a capability they absolutely must verify before sending anyone to Mars. On Flight Day 7, lunar gravity grabs the capsule and acts as a massive slingshot, whipping Orion around the far side and accelerating it back along the free return trajectory toward Earth. During the long fall back home, the crew runs experiments to block deep space hazards. They use whatever equipment and stowage bags they have inside the cabin to build makeshift radiation shelters. Deep space is awash in severe solar weather. Astronauts on long-duration interplanetary flights will inevitably encounter high radiation levels, making these on-the-fly material adaptations critical for their survival. As the mission reaches its vital hours, the crew module separates from the European service module, dropping the dead weight of the propulsion system. The capsule then precisely rotates to point its heat shield forward. Hitting the atmosphere at nearly 11 kilometers per second, the friction generates immense thermal loads. It is the fastest human re-entry ever attempted, pushing the outer heat shield to extreme temperature limits. But the heat shield alone won't save them. Slowing down from those orbital speeds requires a flawless sequential deployment of drogue stabilization chutes, followed closely by the massive main parachutes to gently drop the capsule into the ocean. A splashdown in the Pacific Ocean, followed by recovery by the U.S. Navy, marks the end of the mission's flight phase. Once the crew is safe, engineering teams move into a comprehensive post-mission inspection of the capsule. Teams strip the capsule down, extracting terabytes of data. They inspect the heat shield degradation, analyze the pilot's manual control inputs, and reverse engineer exactly why the water valve closed and the communications dropped out. Every mechanical glitch isolated, and every data point recorded on radiation shielding and life support informs the hardware requirements for multi-year interplanetary travel. This 10-day stress test provides the empirical evidence needed to design the systems that will eventually carry humans toward Mars.